Okay, let's start from the first problem. It says that for the following graph, write down the adjacency matrix. Well, it's obvious, right? I mean, between each two vertices, if there is an edge, then we should write 1. If there's no edge, then we should write 0. And this is a simple graph, so the number of edges between each two vertices is at most 1. For example, in here for the first row, it is for vertex 0. I know that there is an edge between 0 and 1, and also there is an edge between 0 and 2, but there is no edge between 0 and any other vertices. So all the rest of them are 0. For the next one, for vertex 1, it has an edge to 0 and 3, but it doesn't have any edge to any other vertices. And so on. Again, for vertex 2, it only has an edge to vertex 0. For vertex 3, it only has an edge to vertex 1. For vertex 4, it has an edge to vertex 1 and 1 to vertex 5. And 5 has an edge to vertex 4 and 1 to vertex 7. And so on. And we can easily just fill up everything, and these cells for these edges are 1 and the rest of them are 0. You can easily fill this grid. This is a very easy problem. For each I and j, you should just check if there is an edge between I and j or not. If there is, you should, the exact definition of the adjacency matrix is that how many edges is between these two vertices. Maybe there's more than one edge between these two vertices. For example, if you have two vertices and there are 3 edges between them, then you should write 3 in that cell. And that is okay, that is possible. I mean, yes, in simple graphs, we only have at most 1 edge between each two vertices, but in general, it is possible to have more than 1 edge between each two vertices. So that's it about this problem. Now write down the adjacency list. Please source each sublist. Well, for the first vertex, vertex 0, we know that the adjacency list is that vertex 0, as I said, is connected to vertex 1 and vertex 2. Vertex 1 is connected to vertices 0 and 3. Vertex 2 is connected only to vertex 0. So this way we can just find the adjacency lists. This problem is also a very easy problem. For vertex 3, it is only connected to 1. For 4, it is connected to 1 and 5, and so on. Okay, so this way you can just find out to which vertices it is connected and just write them. Okay, so the first problem was very easy. Now let's talk about the second problem. We are using Karatsuba's algorithm. If you don't know what Karatsuba's algorithm is, make sure to watch the video about Karatsuba algorithm. We want to calculate this product: 48,351, 8,709. In what follows, STM means single digit multiplication. Using school book multiplication, how many single digit multiplications will be performed? Well, as I said in that other video, in this school book multiplication, when we have two numbers, the first one has A digits, the second one has B digits, we multiply each digit of the second one and each digit of the first one once, at least once. It's so, this is gonna be the product of the length of these two numbers. For example, if my first number is this, for example, 1, 7, 5, 3, 2, and 6, 5, 7, 4. When I want to calculate the product of these two numbers, first I multiply this 4 by this 2, and I write 8 in here. Then I multiply this 4 by this 3, and I write 2 in here, and I have one additional number that I will add to my next digit. Then I have 4 times 5, which is 20. Then 4 times 7, which is 28. and then 4 times 1 and plus 3, which is 7, and so on. So what I'm saying is that, again, I do the exact same procedure for 7 and then for 5 and then for 6. So I'm saying that for each of these digits, you will multiply it by each of the digits in the other number. So we can say that the number of single digit multiplications is equal to the number of digits in the first number multiplied by the number of digits in the second number. So in here we have 5 digits for this number and 4 digits for this number. So it is 20. Okay. Okay, the next problem, draw the corresponding tree and identify the number of STMs which will be performed. This is a better problem somehow. If you completely understood what Karatsuba is, when we want to calculate this product, first we want to draw the tree. So we want to multiply 48,351 by 8,709. Okay. Okay, what was the first step in Karatsuba? We said that we consider the lengths, and we said there are many different approaches. The approach that is used in this course is to just consider the length of the number with less digits, which is 4 in here. The floor of 4 divided by 2 is 2, so we have to split 2 digits from the ends. Okay, so we divide the length of the minimum length of these two numbers, and we divide it by 2, and we split that much from the end of both numbers. And then we will do this. If you remember, we wanted to say that if we have this A and then B, and in here we have C and D, we will need to calculate AC, BD, and A plus B times C plus D. We have to call these 3 functions. I mean, call the function with these 3 arguments, because we need AC and BD, and if we calculate this and subtract these 2 values, then we're gonna have A then we're gonna have AD plus BC if you subtract AC and BD from this. Okay, so this was just a flashback to what Karatsuba was. If you want to know more about it, I again recommend you to watch that video first so that you're completely okay with this. Well, okay, the next step in here, as I said, is that first we have to calculate 483 times 87. This is A times C. In here we have to calculate 51 times 9. Well, this is 51 times 9 times 09, but that 0 doesn't have any effect. It's a leading 0, so it doesn't matter. And when we multiply these 2, one of them has 1 digit. One of them has only a single digit. So in here, we're going to have 2 single digits multiplications. Why? Because when one of our numbers has only 1 digit, the number of single digit multiplications will be equal to the number of digits in the other number, because we have to multiply this digit to all of those digits at least once. Okay, in here we just do this school book multiplication. So it's going to be 1 times the length of the other one. And the last one is this 483 plus 51 times 87 plus 09 or 9. Well, this is equal to 534, and this is equal to 96. And again, we have 2 numbers. One of them has 2 digits, one of them has 3 digits. So we consider 2, floor of 2 divided by 2 is 1. So we have to split 1 digit from the end. And then we will gonna call the function with 3 arguments. The first one is going to be 53 multiplied by 9. The last one is 4 times 6. Well, in this one we have 2 single digits multiplications. In here we have 1 single digit multiplications. Why? Because one of them has only 1 digit, a single digit. Therefore, Therefore, the number of STMs is equal to the number of digits in the other one. In here, both of them are 1, so it's going to be one single digit multiplication. In here, the other one is 2, so it's going to be two single digit multiplication. And the middle one is going to be 53 plus 4 times 9 plus 6, which is going to be 57 times 15. Both of them have 2 digits, so we have to split with 1 digit. Then we're going to have these 3. 5 times 1, 7 times 5. You see that the leftmost one is the product of the leftmost parts. The rightmost child in R3 is going to be the product of the rightmost parts. The middle one is the product of the sum of these two and the sum of these two. Okay, so that's the rule. The leftmost one is the product of the left ones, the rightmost one is the product of the right ones, and the middle one is the product of the sum of these two and the sum of these two. So the middle one in here is going to be 5 plus 7 times 1 plus 5, which is going to be 12 times 6, which is going to be 2 single digits multiplication. This one is 1 single digit multiplication because both of them have 1 digit. This is 1 single digit multiplication. And we finally get here. Let's circle around these single digit multiplications that we reach in here. So now about these parts. One of them has length 2, one of them has length 3. So we have to split by 2 divided by 2. In here we have 3, we have to call these 3. In here we have 3 times 7, the right parts. In here we have 48 times 8, the left parts. Well, this is obviously 2 STMs. This is 1 STM. And in the middle we have 48 plus 3 times 8 plus 7, which is gonna be 51 times 15. Both of them have 2 digits, so we have to split with 1 digit to the right, and then we're gonna call these 3. 1 times 5, 5 times 1, and 6 times 6. 5 plus 1 times 1 plus 5. And this is gonna be a single digit multiplication. This is gonna be a single digit multiplication. And this is gonna be a single digit multiplication. Okay, so that's all about the tree. So if you want to write the tree, you just need to write this tree like this exactly. Maybe you need to make it a bit cleaner because, and that's okay. You don't even need to. And no, that's okay. You don't even need to make it cleaner than it's clear, So it's clear that what you're doing, this is the Karatsuba's tree. You just write that each function call is with what arguments. And now if you want to just see that what is the number of STMs, it's going to be 2 plus 1 plus 1 4 plus 2 6 plus 1 7 plus 2 9. There's a 1 here as well, plus 1 10 plus 1 11 plus 1 12 plus 1 13 plus 2 15. So the answer is 15 STMs. Okay, so this is the answer to the second question. This one had more work compared to the previous one. Okay, let's solve the next problem. Just for problem context, recall that for Karatsuba we decompose 2 n-digit numbers a and b as a1 a0 and b1 b0, where a0 a1 b0 and b1 each has n half digits. Then we did a modification which resulted in us needing 3 instead of 4 multiplications. That's exactly what I told you about Karatsuba. The whole idea is about just calling the function 3 times instead of 4 times. Then instead of having n to the power of log of 4, which is 2, which is n squared, we're gonna have n to the power of log of 3. Okay, because each time instead of 4 branches, you're gonna have 3 branches. So the whole idea was just needing 3 instead of 4 multiplications. of about n-half digits each, there were also theta of n worth of additions, subtractions, and shifts. This gave us the recurrence relation T of n equal to 3 T of n-half plus theta of n, which has solution theta of n to the power of log of 3 equal to theta of n to the power of 1.58 by the master theorem. Suppose we create a new version called Karatsuba 4 in which we decompose the two n-digit numbers a and b as a3, a2, a1, a0 and b3, b2, b1, b0, where the ai and bi each has n fourth digits. Suppose we do a modification which results in us needing 13 instead of 16 multiplications of about n fourth digits each. Show that the asymptotic time complexity will be worse than Karatsuba explained. Okay, well, in here again, we just need to first write the recursive equation. T of n in here is equal to 13 calls of multiplication for numbers of length n fourth, right? So it's going to be 13 times T of n fourth plus some theta of n for addition, shifts, subtraction, etc. So this is going to be my recursive formula. And how can I find out what exactly it is? I can use master theorem. And by using master theorem, you can easily see that T of n is going to be from theta of n to the power of log of 13 in base 4. And it is going to be worse than n to the power of log of 3. Because log of 3 in base 2 is equal to log of 9 in base 4. So log of 13 in base 4 is more than that. Okay, so I mean it's obvious that it is more than that. Because log of 9 in base 4 is equal to log of 3 in base 2. I mean log of nx in base 2 is equal to log of x squared in base 4. Right? So anyways, but it is not important. You can also calculate it. And you can see that it's going to be around n to the power of 1.85. Just using calculator, and this just tells us that the answer is going to be worse than what we had in Karatsuba. The next one, suppose we do a modification which results in needing 6 instead of 16 multiplications. Show that the asymptotic time complexity will be better than Karatsuba. Well, again, the exact same thing. T of n is going to be, this time instead of 13, we're going to have 6 times T of n fourth, again plus theta of n. Why? Because again we have some additions and shifts, and because this 6 is more than this 4, using master theorem, it tells us that T of n is going to be theta of n to the power of log of 6 in base 4, okay, which is better than log of 9 in base 4, so it is better than Karatsuba. You can also use a calculator and you can see that it's going to be equal to theta of n to the power of around 1.29, which is less than what we had before. If you're not completely okay with master theorem, make sure to watch the other video about the master theorem. The master theorem is very important. You can find the intuition behind it. I mean, even if you don't know the master theorem, you can find out what your time complexity is. If you want me to explain that, it's just, for example, in here you have 60 of n over 4. So each time, each layer that you go downwards, it's going to be 6 branches, but n will be divided by 4. So how many layers do you have if you go like this? The number of layers, the number of times you go down, it's going to be log of n in base 4. How many leaves do you have in your last level? It's going to be 6 to the power of this, because each time you will have 6 branches. So this is going to be number of leaves, and this is easily equal to 6 to the power of log of n in base 6 to the power of log of n in base 4 over log of n in base 6. And this is equal to n to the power of log of n in base 4 divided by log of n in base 6, which is going to be log of 6 in base 4. So anyway, even if you don't know master theorem, you can calculate it by yourself. But it's better if you know master's order. Maybe you can't calculate it by yourself at the time that you face such a problem. So it's better if you completely know master's theorem. And it's just a simple comparison. You just compare this number with this number and you find some results based on that. What is the maximum number of multiplications m we could allow in order to be faster than Karatsuba? Explain. Well, in here t of n is going to be equal to, we call it m, okay, the maximum number of multiplications that we can allow. This is going to be equal to m times t of n over 4 plus theta of n, okay. And we know that m is going to be at least 6, because 6 is okay. We saw here that 6 is okay. So m is going to be greater than 4. And how does that help? That helps us because this shows that based on Master's theorem, t of n is going to be theta of n to the power of log of m in base 4, right? So we have this. So log of m in base 4 needs to be better than log of 3 in base 2. When I write LG, it means that my base is 2. And you know the base 2 and base 2 and base 4 are very similar. As I said, when you want to see what is it in base 4, you can just say that it is gonna be in base 4 of the squared of this number. So it's gonna be log of 3 in base 2 is gonna be equal to log of 9 in base 4. Why? If you really want me to explain you why, I will tell you right now, and if you don't want, just skip this part. Well, the reason is that log of any x in base 2 over log of x in base 4 is gonna be log of 4 in base 2, which is 2. So we know that log of anything in base 2 is twice its log in base 4. So we can say that log of any x in base 2 is going to be equal to 2 times log of x in base 4. And when you multiply logarithm by 2, it's just like log of x in base 4 plus log of x in base 4. And we know that when we add two logarithms, it's like we multiply the value inside. So it's going to be log of x squared in base 4, right? So this way we can just see that log of x in base 2 is equal to log of x squared in base 4. Another intuitive way to say that is that we can just say that what is log of some x in base 2. It means the number, let's call it k, that it means that 2 to the power of k is equal to x, right? Now, I want to show that 4 to the power of k is equal to x squared. Well, this is very simple. When 2 to the power of k is equal to x, 4 is equal to 2 to the power of 2. So, I mean, it's like instead of 1, 2, you have 2 2's. Instead of any 1, 2, you have 2 2's. So, when instead of 2 to the power of k, you have 4 to the power of k, if 2 to the power of k is x, 4 to the power of k is x squared. So it means that this means that log of x in base 4, x squared in base 4 is equal to k again. So these two are equal. This is another intuitive way to say that these two are equal. But anyways, this is just something that we know. Well, what we can say is that instead of log of 3, we just consider log of 9 in base 4 and we compare it with m. Log of m in base 4 should be strictly less than log of 9 in base 4. So m should be at most 8. So if it's asked that what is the maximum number of multiplications m, it is going to be 8. So the answer to this problem is 8. Okay, let's move on to the next one. Following on the previous problem, suppose instead that we create a new version called Karatsuba K. Following on the previous problem, suppose instead that we create a new version called Karatsuba K, where k is an integer greater than 3, in which we decompose the two n-digit numbers a and b as a k minus 1 to a0 and b k minus 1 to b0, where a sub I and b sub I have n over k digits each. So instead of splitting into 2 parts or 4 parts, you this time split into k parts. Okay, so this gives you some intuition about what's going on. Each time, instead of going from n to n half or n fourth, you will go to n over k. Now it says that assume m is greater than k, but when it says that m is greater than k, what can I conclude? You know, the main thing in here is that when m is greater than k, I know that if I use master theorem, the result is going to be n to the power of log of m in base k when m is greater than k. So this is very important. If m was less than k, then the number of those leaves at the last level wouldn't matter. So the only thing is that if you completely know what master theorem is, this m greater than k gives you a very important information. So assuming m is greater than k, find an expression for the maximum number of multiplications m we could allow in order to be faster than k. Suba explain. Well, in here, as I said, we have T of n equal to, first let's write the recursive formula. We have this. Well, theta of n is always there. That's because of shifts and additions. We have only constant additions or shifts, and each one of them take theta of n time. So when we have all of them, it's just going to be theta of n. Okay, so we have some constant, for example, 4 or 5 or 6, some constant number of adds and shifts, and each one of them take theta of n. So in total, it's going to be theta of n, and we're going to have m times t of n over k. And as I said, when m is greater than k, based on master theorem, we're going to have that t of n is going to be from theta of n to the power of log of m in base k. Okay, because in those branches, these branches, you know, the intuition behind it is that the number of branches is that much that the number of leaves will be a lot, and that would show our time complexity. It doesn't matter, so you can just memorize master theorem. T of n is equal to this. Okay, now we know that n to the power of log of m in base k should be less than n to the power of log of 3 in base 2. So we want to find the maximum m with this situation. So this says that log of m itself in base k should be less than log of 3. That's the only way. The power should be less. So in here I can just say that log of m in base k is less than log of 3, and if we only consider these two numbers, if on both sides we have k and we have k to the power of these two numbers, in here we have k to the power of log of m in base k, which definitely gives us m based on definition of logarithm, k to the power of log of m in base k. So based on definition, that should be m. Otherwise this wasn't log of m in base k. And in here we have k to the power of log of 3. Okay, and when we compare these two, this should be less than this. So m should be less than k to the power of log of 3. M should be the greatest integer less than k to the power of log of 3. Now, can we say that m is at most floor of k to the power of log of 3? Well, no, that's not correct. Because floor is the greatest number less than or equal to something. I mean, floor of some number which is not necessarily an integer. The floor of some number is just the greatest integer less than or equal to that. But here we want the greatest number less than this. When you want it to be less than this, we want the greatest integer less than something, you have to consider the sale of that number, which is the first number greater than or equal to this, the first number which is bad. You have to see what is the first number which is bad. What does bad mean? It means that this number is not anymore less than this, which means that it is greater than or equal to this. So we should consider the sale, the first number greater than or equal to this. Okay, so we consider the sale. This is the first number which is bad. So if you subtract 1 from it, it is the last number that was good, because the previous number was the last one which was good. So m is at most this. This is not floor of k to the power of log of 3. It is the sale of k to the power of log of 3 minus 1. Because, as I said, if you want the greatest integer less than some x, the greatest integer less than some x is gonna definitely be log of x is gonna definitely be sale of x minus 1. Because sale of x is the first integer greater than or equal to something, so the previous integer was less than that. Okay, this was the fourth problem. The next one, given the following graph, fill in the following. How many walks are there from vertex 0 to vertex 5? When we have walks, walks can have duplicated edges and vertices. So when we have this, when we have a walk, you can just consider an edge and just go there and go back and then go there again and go back and just be here as long as you want. And then at the end go to 5. Because there's no limits on how many times you pass over an edge. You can just pass them as you want. It doesn't set any limit on the length of the walk. So it can be from any length. And so there are infinite possibilities. So this is going to be infinity. The next part, how many paths are there from the vertex 0 to vertex 5? Well, I don't really like this problem. This is just something that you should go into it and just count everything. Well, when you encounter a problem like this, that you just need to count something, I recommend you to categorize everything. Then it would be easier for you to find the answer. I mean, you start from vertex 0, then in your first step, you either go to vertex 1 or go to vertex 2 or go to vertex 3. So it's like we have 3 categories of paths. The ones that first go to vertex 1, the ones that first go to vertex 2, and the ones that first go to vertex 3. So first, let's only consider the paths that start from 0 and first go to vertex 1. Okay, let's just focus on this category. So the first one is 0, 1, 2, 5. The next one is 0, 1, 2, 4, 5. 0, 1, 2, 3, 5. And well, definitely when the first one is 0, the next one is 1, the next one should be 2. And then we are at 2, we either go to 4 and then go to 5, or we go directly to 5, or we go to 3 and then go to 5. So it seems like we saw everything and every path is covered. The next category, it starts from 0, 2. We first go to vertex 2. But when we go to vertex 2, then we can go to, for example, vertex 3, and then we can go to vertex 5, 0, 2, 3, 5, 0, 2, 4, 5, and 0, 2, 5. It's very similar to the previous case, because when we are at 2, then we just have these 3 cases. Either go to 3 or 4 or 5 directly. The last category is that if from vertex 0, we will go to vertex 3. If we go there, then from there, we again have some cases. Either we go directly to vertex 5, or we will go to vertex 2, and then from there, we will go to vertex 5, or we will go to vertex 2, and then from there we will go to vertex 4, and then 5. If we go directly to 5, it's just this. If we don't go directly to 5, we should definitely go to vertex 2, because we don't have any other neighbor other than 0. So we should go here, and from here we just either need to go directly to 5 or go to 4, and then from 4 to 5. So again, we can be sure that we calculated every case and we're sure about this, it's always good to check everything again at the end when you have to count something. Categorizing really helps. It really helps you to find all the ways when you split the solution into different categories, then you can see everything. And in this way, we can just say that this is 9. Okay, the next one, how many cycles are in the graph? Again, you have to count everything. What I recommend is that you pick a vertex, just see in how many cycles this vertex is, and then remove that vertex. And just see that in the rest of the graph, how many vertices are there. Well, I think it's not a bad idea to consider this vertex, vertex 2, and see that in how many cycles vertex 2 exists. So one of them is 2, 1, 0. These 3 vertices. Do not forget that a cycle is a closed path. A walk can have duplicated vertices or edges, but a path cannot have duplicated vertices or edges. And also, a cycle is just exactly the path, just the first and the last vertices are the same. I mean, you end up where you started. Okay, so for example, if you consider this is a path. Every vertex is visited once, and every edge is only visited once as well. The only difference with path is that in path, the first vertex and the last vertex are not the same, but in cycle, the first and the last vertices are the same. So this was the first cycle. As I said, it's good to try to categorize things. So let's see that what else can we have with 2, 1. From 1, we can go to 0. There is no other choice. And from 0, if we do not go to 2 again and end the cycle, we have to go to vertex 3, and from there we can end the cycle. I mean, you can also consider another 2 at the end of them as well. That's okay. I mean, that doesn't make any difference. I'm just not adding that vertex anymore. I'm just saying, okay, there is a cycle between these 3 vertices. So I won't add that. But anyway, the next one is 2, 1, 0, 3, 5, and then from 5 I can go to 2. The next one is 2, 1, 0, 3, 5, 4, and 2. Okay, so it seems like there are all the walks with 2, 1. Now we have to see what are the walks with 2, 4. With 2, 4, either we go to 5 and we're done. From 5 we will go back to 2. Or we have 2, 4, 5, 3, and then we will go to 2. I write the rest here. We have 2, 4, 5, 3, 0, and then we will go to 2. You might say that we can also do 2, 4, 5, 3, 0, 1, but that is going to be the same as what we had in here. So there's no difference between these two. And as I said, we don't need these 2's at the end as well. And if we have 2, 3, we either have 2, 3, 0 or 2, 3, 5. And I think nothing else, because when we go to 3, we have to go to one of the directions. And when we go there, we should either end. If we do not want to end, we have to go to the other vertex in here, which is counted. This cycle is counted already. And then there's one additional case when from 2 we'll go to 0, and then 3, and then 5. This is an additional case as well, which is gonna form this cycle. If we go from 2 to 5, we either go to 4, which is counted, or we go to 3 and then to 2, which is counted, or then we go to 3 and then to 0, then to 2, and that one is counted as well. So anyway, it is going to be counted, and that doesn't add any new cycle. And when you remove this vertex 2, the beauty is here. And now that we saw all the ways that we can have a cycle including vertex 2. Now we can remove vertex 2 and then see the rest of the graph. If we remove the vertex 2, then the rest of the graph is like this. I mean, it's like a pass. Obviously, it doesn't have any other cycle, right? So the point is that the vertex 2 was a very critical vertex. So you could easily say that if you remove vertex 2, there is no cycle. So it's easy. Without vertex 2, we can easily count the number of cycles. It's 0. So if there is a vertex set, by removing it, you can easily count the number of cycles. Then it's going to be so easy. You remove it and it's 0 plus the number of cycles that 2 is in it. So now you just need to find that how many cycles vertex 2 is in it. So anyway, the answer is going to be 10. This way we had 10 different cycles in total. Okay, the next problem, suppose a collection of people is confronted with a table full of sandwiches. Each sandwich has been cut in half and each half sandwich has a tag with a person's name on it. We run the following pseudo sandwich code. For each person says delicious, person goes to the table for each half sandwich with person's name on it. Person yells delicious, person eats the half sandwich, and okay, so the first thing, let's just consider that this is delicious 1, this is delicious 2. Okay, the number of times that we hear delicious, how many times will delicious be spoken? So this question is that how many times delicious 1 will be spoken plus how many times delicious 2 will be spoken, right? So the first thing that really helps us to see what is going on is to find out that there are 2 types of delicious. Even though it seems like they're a nested loop, and when you have a nested loop, you have to multiply something. This is not like that, because we have 2 types of a person saying delicious, and any of the times that delicious will be spoken, it is in one of these 2 categories. It is from one of these 2 forms. So if we consider that how many times delicious 1 is called and how many times is said and how many times delicious 2 is said, we can just add them up. Well, how many times delicious 1 will be said? It's obvious, P. Because we have P people. Each one of them say it once, so it's going to be P in total. How many times this one will be delicious 2 will be said? Well, we have S sandwiches. Therefore, we have 2S half sandwiches. And each half sandwich will be eaten only once by one person. There's a name of one person on it. So each half sandwich will be eaten once, only once. Therefore, we have 2S half sandwiches. Each of them will be eaten exactly once, and for each one of them we hear delicious once. So it's like 2S times 1. For each half sandwich once we hear that. For each half sandwich we hear that once. So in total, when we have 2S half sandwiches, it's going to be 2S. So the answer to this one is P plus 2S. That's all. This was very easy. This is also a very easy problem. If you just comprehend what it is about, that's when delicious. I think that maybe this problem is designed so that you can, figure out this paradox between that these 2 are in a nest, that these 2 are in a nested shape, but on the other hand, they shouldn't really be multiplied by each other. I mean, each deletion is either this or this. This is this or this. So we should add these 2 values. Okay, the next problem. Suppose A is the n by n adjacency matrix for the graph, and suppose that I and j are fixed vertices. Explain why A of I and j equals the number of walks of length 1 from vertex I to vertex j. Well, In this problem, I think the author of this problem assumed that the graph is simple, is a simple graph. But let's even not consider that. I mean, we can even not consider that. A simple graph, as I said in my graph video, is a graph that there is at most one edge between each two vertices. But it's not always the case. We can have more than one edges between two vertices. I mean, in real world problems, it's like we have two cities and there are multiple roads between them. That's okay, it's possible. So in real world, it's not like always between each two vertices there's at most one edge. You can have more than one edge. And then the adjacency matrix between vertices I and j, if there are, for example, 3 edges, we should write 3 in here. Okay, so I will not assume that each cell is either 0 or 1, even though I think in this problem you can assume that, but it's not even needed. I'm gonna solve it for the general case, okay? Okay, so a of I and j, what is a of I and j? A of I and j is the number of edges between I and j, right? In a simple graph, this is either 0 or 1, because there is either 0 edges between I and j, or there's 1 edge between I and j. Either there's no edge or 1 edge. But it's even possible that there are 2, 3, 4. So a of I and j is the number of edges between I and j. On the other hand, the number of walks of length 1 between I and j, a walk of length 1 means a walk with only one edge. So when you have a walk of length 1, you only have one edge. If you start from I and go to j with length 1, it means that you have only one edge. What does it say? It just says that the number of walks from I to j with length 1 is also equal to the number of edges from I to j. So a of I and j is equal to the number of edges from I to j. And also the number of walks of length 1 between I and j is equal to the number of edges between I and j. So both of them are equal to the number of edges between I and j. So both of them are the same number. Both of them are equal to the number of edges between I and j. So this is solved. For the second part, you have to now prove that for any value of k, for the second part, it says that for two n by n matrices, A and B, we can define the n by n product matrix AB, which has the property that I and j entry is calculated by AB of I and j equal to this formula. I will explain that, what exactly this means. Using this fact, prove by mathematical induction that a to the power of k of I and j equals the number of walks of length k from vertex I to vertex j. You did the base case in A, so all you need to do is the inductive step. Well, it completely is saying that's what you should do. You need to use induction. If you're not familiar with induction, make sure to watch my video about induction. That gives you some insights. If you're not familiar with matrices and what matrix multiplication is, what matrix product is, watch the video about matrix product. But anyways, I'm gonna first explain what matrix product means and why that this is just the general form of the problem A that we have had in here. Because in here we had A of I and j, we were talking about A. A is A to the power of 1. I mean, everything to the power of 1 is itself, is only itself. So in here we showed that for k equal to 1, it is correct. So when our k is equal to 1, a to the power of k of I and j is really equal to the number of walks of length k. In here we showed that a to the power of 1 of I and j, or a of I and j, is equal to the number of walks of length 1 between I and j. So now in here we want to say that a to the power of k of I and j is equal to that. So we want to show that for each k this is equal to that, okay? So first let's talk about matrix products. What is the meaning of matrix product? Well, matrix product is just this. We have two matrices. Let's just consider both of them are n by n, which is needed in this problem. Matrix product means that the answer, I just show the matrix with a table, with a grid, because matrix is nothing. Matrix is just a table. Okay, an n by n table. So all of these are n by n. Their sizes are equal. So when you calculate the product of two matrices, what we can say is that cell number I and j, this cell, is equal to, if we consider the row number I from the first matrix and the column number j from the second matrix, if we consider this row and this column, well, this row has n numbers and this column also has n numbers, right? So this row has n numbers and this column has n numbers because both of the matrices are n by n. So you have n numbers here, n numbers here. You just multiply the first number from here by the first number from here, the second number from here by the second number from here, and the nth number from here and the nth number from here. So basically, if you see what is going on in here, AB of I and j, you see that all of the numbers, you can see that all of the cells from A are from row number I. You can just see it here. All of the cells from A are from row number I. And all of the cells from matrix B are from column number j. You can just see this in here. So in here you're just considering row number I, in here you're just considering column number j. So it's like you're just saying that AB of I and j is equal to sigma of k from sigma of, for example, x from 1 to n equal to sigma, for example, x equal to 0 to n minus 1, a of I and x times b of x and j. So this number x from column number I of a times the elements number x from the jth column of B. So we have two sets of n numbers. We calculate the product by multiplying the first number from here by the first number in here, and so on. So this is how, if we add up these numbers, we will get what is the value in here. Okay. This is just nothing. You consider a row from here and a column from here, and you just multiply these two. They are both n numbers. You multiply the first one from here and the first one from here, the second one from here and the second one from here, and so on. Okay. So let me erase all these. So we did the inductive base. Now we need inductive step. We know that for k something is correct, is true. We want to show that for k plus 1 it is always true. Now you might ask that why for k is true when we showed that for k is true. And then I strongly urge you to watch my video about induction. Okay, this is assumption. This is assumption. It says that if for k it's true, then for k plus 1 is true. Okay, it just says if for k is true, then for k plus 1 is true. This way we form a chain. If for 1 it's true, then for 2 it's true. If for 2 it's true, then for 3 it's true. If for 3 it's true, then for 4 it's true. If for 4 it's true, then for 5 it's true, and so on. So this is a fucking assumption. Okay, we just say that if for k is true, then for k plus 1 is true. So you don't need to show that for k it's true. You just assume that for k is true. You're just saying that if for k is true, then for k plus 1 is true. For example, if it is raining, then you do that. Do you need to show that it's raining? No, you're just saying that if it is raining, then you should do that. Okay? So what you're saying in here is that if this happens, if then for k plus 1 this is always correct. So you assume that, you don't need to show for k. You know, I showed it with dominoes in my other video about induction. You're just saying that if this domino falls, then the next one falls. You don't really care if this one falls or not. You're assuming that this one falls. You're assuming that this one falls, and you set the next one in a way that if this one falls, that one falls too. And then at the end, you just push the first one, and then all of them will fall. So the whole point is that instead of for each of the dominoes you prove independently that this one will fall, you just form a chain in your mind and you say that, okay, if this one falls, then the next one falls. And then you just push the first one, and you can make sure that all of them will fall, because you form this chain. So this is just for making the chain. I want to say that if for k it is correct, then for k plus 1 is correct. I'm just saying if. If for k is correct, then for k plus 1 is correct. Okay? So you don't need to prove it for k. I see it many times that people ask, yeah, but why? Why for k is correct? You don't need to show that for k is correct. It's just a if. You don't need to show that. So anyway, we assume that for k is true. And if you ask in the comments below that why for k is true, I will block you. We know that for a to the power of k of I and j shows the number of walks of length k from I to j. Now we want to say that for k plus 1 is also true. If for k is true, for k plus 1 is also true. And k in here is just a variable. Maybe it's better if you use another variable, because k is used here. So let me change my variable. I'm just doing it because k is used, and it's better if you do not use k again. It makes us confused. We just showed that if k is equal to x, then it is correct. Now we want to show that if k is equal to x plus 1, then it is okay too. It means that for a to the power of x of I and j, it shows the number of walks of length k, right? Of length, x. Now here we have a to the power of x plus 1 of I and j, and we want to show that that one is correct as well. We want to prove it for every k, but instead of proving for every k, we assume that for k equal to x is true, and x is at least 1. Now we want to show that it is also correct for k equal to x plus 1. If for k equal to x it is correct, then for k equal to x plus 1 this is also correct. Okay, we want to just show that. Well, how do we say that? Well, a to the power of x plus 1 is equal to a times a to the power of x, right? It's the product of these two matrices. Therefore, we can say that a to the power of x plus 1 of I and j is equal to sum of, for example, L from 0 to n minus 1, a of I and L times a to the power of k of L and j. Sorry, x and L and j. Okay, so a to the power of x plus 1 of I and j is equal to this. Well, what's the intuition behind this? Well, the whole intuition is that a walk of length x plus 1 is equal to a walk that you first go one edge and then you're gonna have x additional edges. So if you have x plus 1 edges, it means that first you have one edge and then you have x additional edges. That's the whole point. If I'm gonna go from here to there with x plus 1 steps, it's like first I do my first step, and then from there I will have more additional x steps. So that's the whole idea. I want to count the number of walks, for example, with length x plus 1 from I to j. What I can say is that, okay, where do we go with the first edge? For example, either I go to vertex 0, or I go to vertex 1, or I go to vertex 2. I go to some vertex. And then from there, I will have x additional steps to reach j. So first, from I go to one of its adjacent vertices. It can be from any edges. If I will go to some vertex L, I should just see that how many edges are there between I and L, which can be either, in a simple graph, it is either 0 or 1, or in the general form, it can be any number, any integer number. So we have some edges from I to L. It is the number of ways to go from I to L with one step. And then from L, we see that how many ways do we have to go from L to J with x steps. So this way I formed a walk of length x plus 1. A walk of length x plus 1 is equal to a walk that I first go one step with one edge, and then from there I will have x additional edges, x additional steps. So that's it. Why I multiply these two numbers? Because, for example, if I have 3 edges here, for each of these 3 edges, and each of these walks here, for example, there are, I don't know, y number of walks of length x, we assume that a to the power of x of li and j is equal to that, is correct, is equal to the number of walks of length x. So if this is y and this is, for example, 3, then we have 3 y ways. Why? Because each one of these gives us y ways. We have 3 of them, so it gives us 3y. So anyway, we need to multiply this by this. And we have to add all these values. Why we have to add all these values? Because any vertex can be vertex L. Any of the vertices can be our vertex L. In our first step, we can go to any of these vertices, and then from there we can go to our destination. So we should calculate the sum of all of them, and that's all. So I can say that if by the inductive hypothesis this is equal to the number of walks of length x and this is equal to the number of walks of length 1, if we concatenate these two, we're gonna have a walk of length x plus 1. So this gives us all the walks of length x plus 1 from I to j. So if it is correct for k equal to x, then it is correct for k equal to x plus 1. For example, if it is correct for k equal to 1, then it is correct for k equal to 2. If it is correct for k equal to 2, then it is equal to k for equal to 3. So it's like, again, we have some dominoes. And we know that if for 1 is true, then for 2 is true. If for 2 is true, then for 3 is true. If for 3 is true, then for 4 is true, and so on. Then if we show that for 1 is true, then for all of them is true. And we're done. So this is how you can solve the last problem as well. That was all about homework 8. If you had any suggestion, you can drop your comments below. If you had any questions, you can ask them below as well. And I will try to answer all of them. So feel free to ask any questions. Take care. Shaya.